Welcome back, everyone. Today's explainer is tackling what is easily the greatest structural mystery of our entire universe: dark matter. And I'm incredibly excited to guide you through this, because we are looking at a puzzle that literally rewrites our basic understanding of reality. We're going to dig into the hard technical evidence, trace the history of how this was even discovered, and look at exactly how scientists today are trying to catch a ghost. Just a quick look at our roadmap for today. We'll start by uncovering the first historical clues of this invisible mass, then move to the modern macro-scale cosmic evidence. After that, we'll look at how it acts as the universe's scaffolding, profile our prime dark matter suspects, and finish up with the intense, deep underground search happening right now. All right, let's jump right into part one, uncovering this invisible mass and tracing the very first clues. The idea that there's some sort of unseen mass out there didn't just pop up overnight. It was a really slow realization, driven basically by the math simply not adding up. Way back in 1884, Lord Kelvin first inferred the presence of what he called dark bodies by studying stellar velocity dispersions, which is essentially just looking at how fast stars were moving near our sun. Decades later, Jan Oort hypothesized unseen mass in the galactic plane. But the real wait-a-minute breakthrough, that came in 1933 with Fritz Zwicky. Zwicky mathematically proved, using what's called the viral theorem, that the visible galaxies in the Gamma cluster absolutely could not generate enough gravity to hold the cluster together at the insane speeds they were moving. The gravitational pull of just the visible stuff was way too small. A massive amount of invisible matter literally had to be there, or the whole cluster would just fly apart. That brings us to part two, where we zoom out to the macro-scale crime scene. Fast forward to the 1970s, and astronomers like Vera Rubin started noticing that the outer edges of spiral galaxies were rotating way too fast. Their flat rotation curves were definitive proof that massive halos of invisible stuff surround these galaxies. And this perfectly aligns with our current lambda CDM consensus model, which honestly is mind-blowing. It tells us that everything we can actually see, all the planets, the stars, the dust, the gas, makes up just 5% of the universe. Just 5%. Meanwhile, dark matter makes up almost 27% of the universe's mass energy content. But obviously, how do we know what's there if we literally can't see it? Well, if you want smoking gun physical proof, look no further than the Bullet Cluster. This is the massive aftermath of two huge galaxy clusters smashing into each other. During the crash, the visible hot gas from each cluster slammed together and was slowed way down by electromagnetic interactions. But when we mapped the gravity of the area, it showed that the bulk of the mass, the dark matter, completely separated from the gas. It passed right through the collision without interacting at all. It didn't slow down, it didn't crash, it just kept on going. So how exactly did we map that invisible gravity? Through something called gravitational lensing. According to general relativity, massive objects actually warp the fabric of spacetime, which bends the light of distant background galaxies. So even though dark matter doesn't emit any light itself, we can map its exact location and density by watching how it bends and distorts the light behind it into these distinct visible arcs. It's basically acting as a giant, invisible cosmic lens. And the evidence goes back even further. Dark matter leaves a totally distinct fingerprint on the cosmic microwave background anisotropies. These are those tiny temperature fluctuations in the ancient radiation left over from the Big Bang. By studying these ripples, cosmologists can clearly see dark matter's gravitational imprint. It proves this invisible mass was there, heavily influencing the universe long before the very first stars even formed. Which leads us perfectly into part three, the scaffolding of the universe, and how this all forms the cosmic web. Understanding what this invisible mass actually does is absolutely crucial, because without it, the cosmos as we know it simply wouldn't exist. I want you to imagine a giant invisible skeleton. Dark matter acts as the vital gravitational scaffolding upon which the entire visible cosmic web is built. It is quite literally the hidden architecture of the cosmos. Think about the intense heat right after the Big Bang. Ordinary matter was ionized and just blasted apart by radiation. It couldn't clump together to form anything. But dark matter? It's completely unaffected by radiation. So it was able to clump into these dense blobs super early in cosmic history. Over billions of years, those blobs stretched into vast, narrow filaments across the universe. Its immense gravity then acted like a sink, pulling ordinary, visible matter into the nodes of this web, which finally allowed galaxies and massive superclusters to form. Okay, part four. Now that we know this scaffolding is out there, we have to profile our dark suspects. What exactly is this stuff? This is the multi-billion-dollar physics question. First off, we have to differentiate between baryonic matter, which is the ordinary stuff we're made of, like protons, neutrons, and stars, and non-baryonic matter. We know for sure dark matter is non-baryonic. Why? Because if it were ordinary matter, it would have totally altered the formation of elements right after the Big Bang, changing the chemical makeup of the universe in ways we just don't observe. So it has to be something entirely different, something that completely ignores light. Now, we categorize these non-baryonic suspects into cold, warm, and hot candidates. And this is based strictly on how fast the particles move, or what physicists call their free streaming length. Hot dark matter moves incredibly fast, meaning it would smear out small structures and cause giant superclusters to form first. But when we look at deep field observations, we see that smaller galaxies actually formed first and then clumped into clusters later. Because of that, the overwhelming consensus is that dark matter must be cold, moving slowly enough to allow those smaller structures, like galaxies, to form early on. While a lot of scientists suspect it's a yet undiscovered subatomic particle, there is one fascinating macroscopic suspect on the non-baryonic side: primordial black holes. These are hypothetical black holes that would have formed from super dense pockets of matter, collapsing mere fractions of a second after the Big Bang, way before any stars existed. They are still a highly valid candidate for what dark matter might be made of, and they've actually seen a massive surge of renewed interest lately, thanks to new data from gravitational wave detectors and the James Webb Space Telescope. Now, I know what some of you are thinking. We have to address the elephant in the room. What if our laws of gravity are just wrong? Some skeptics propose modified gravity theories, like MOND, or modified Newtonian dynamics, instead of inventing unseen particles. But here's the issue. While those theories can explain certain isolated things like galactic rotations, they severely struggle to mathematically explain the massive array of observational evidence we just talked about. They can't explain the clear separation of mass in the bullet cluster or the specific patterns in the cosmic microwave background. They just don't cover the whole shebang. So, if it is a particle, how are we looking for it? That brings us to our final section, the deep underground search. Consider this for a second. Even though the local density of dark matter in our specific neighborhood of the galaxy is relatively low, there is still roughly a large asteroid's worth of it, about 10 to the 17th kilograms, inside our solar system out to Neptune. That literally means millions of these ghost particles are passing right through your body every single second, completely unnoticed. No big deal, right? To directly detect the leading particle candidates, which we call WIMPs, or weakly interacting massive particles, physicists rely on extreme underground detectors. They bury giant vats of liquid xenon deep inside mountains to shield them from everyday cosmic rays. The hope is that as a WIMP flies through the Earth, it might occasionally, just by pure chance, bump into a xenon nucleus. This tiny microscopic collision would release a faint flash of scintillation light or tiny electrical charge, which highly sensitive tubes around the vat would then pick up. But here's the catch, and it's a huge technical hurdle. It's known as the neutrino floor. At this extreme level of sensitivity, background solar neutrinos, which are just normal, everyday particles emitted by our sun, start triggering the detectors. And they do it in a way that perfectly mimics the dark matter signals we're desperately trying to find. It is an absolute nightmare trying to separate the incredibly rare dark matter signal from this dense, confusing fog of neutrino noise. It's the biggest challenge current detectors are facing. As our detectors plunge deeper into that neutrino fog, and our telescopes peer further back into the cosmic web, it really leaves us with a profound thought. If the very scaffolding of our universe is entirely invisible, making up the vast majority of all the matter in existence, what other unseen structures, forces, or strange phenomena are just waiting out there to be uncovered in the dark? Thank you so much for joining me for this Cosmology 101